Hello everyone and welcome back. I'm Joe Chappelle and you're listening to episode 34 of the OBGYN podcast. Now I've been working on this topic for a while, so I'm very excited to get it out to you all. And as with most of these, what I thought I could do in one episode will probably need two. But today we're going to be delving into the world of aneuploidy screening from its humble beginnings with spina bifida to sequential and integrated screening. The second episode will focus on cell-free DNA and invasive testing, but for now, let's get started with episode 34, Aneuploidy Part 1. Aneuploidy, or an abnormal number of chromosomes, is a relatively new finding in medicine. We can trace its foundation back to Langdon Down in 1866. He was one of the first people to really characterize people with mental deficiencies, and he found a subgroup with a characteristic set of facial features that he described as mongoloid, for what he perceived as a resemblance to East Asian features. This grouping led to many different hypotheses as to the possible nature of the syndrome, ranging from environmental to hereditary and everything in between. The only things that these theories had in common was that they were all wrong. But it wasn't until the 1950s that we got the first clue as to the real underlying etiology. This breakthrough was made possible by the new technology known as karyotyping. Now, we have known about chromosomes since they were first discovered in plant cells in 1842, but there wasn't a consensus on even how many humans had until 1956. Because it was in that year that Joe Tiho, an Indonesian scientist working in Lund, Sweden, perfected his technique for preparing and analyzing chromosomes, and determined that we have exactly 46 chromosomes in 22 diploid pairs and 2 sex chromosomes that differ by gender. More than his discovery, it was his technique that really changed things. Now labs around the world had a reproducible method for analyzing chromosomes. This led to a number of groups all publishing their findings that mongoloids had an extra chromosome. This chromosome would end up being assigned number 21, and the name Trisomy 21 arose to define the syndrome. Now, a slight aside in the original name. As early as the 1950s, many people had a problem with the term mongoloid. In 1965, the Mongolian People's Republic asked the WHO to drop the term. In its place, people looked to the original descriptor and renamed it Down syndrome, and then in 1975, the NIH dropped the possessive and turned it into Down syndrome. Today, Down syndrome or Trisomy 21 are acceptable terms, and I think that we are all grateful to lose that original name. Well, now that we knew what the cause was, so what? Some doctors wanted to be able to offer termination for women carrying a fetus with aneuploidy, but to do that, we needed to find a way of obtaining fetal cells for karyotyping. Now, the obvious choice was amniocentesis, so let me take a minute and describe the origin and the process up to the 1950s, and like I said, we'll get more into invasive testing in the second episode. But amniocentesis had first been performed in the 1870s to remove excess amniotic fluid in women with polyhydramnios. In the 1930s, Menes, Miller, and Haller were injecting dye into the uterine cavity to determine the location and size of the placenta, and in the 1950s it was used to look for high drops due to Rh incompatibility. Well, it was around this time that Dr. Barr from Canada discovered the presence of small cellular bodies in human cells that he called Barr bodies. These turned out to be the condensed chromatin of the extra X chromosome in women, and it allowed us a way of determining sex because men only had one, and therefore no Barr bodies. And so if the cells had a Barr body, then we knew the fetus was female. This was applied to amniocentesis in 1956 by Fritz Fuchs and Paul Rees, and the age of genetic amnios was born. This information was used to determine fetal sex when the mother had X-linked diseases like hemophilia or Duchenne's muscular dystrophy. And for the next decade, this was about all the information we could get from the few cells that were obtained by an amnio, because no one had come up with a reliable method to culture them. But then, in 1966, Mark Steele and William Bragg were able to do just that, and a whole new avenue of research was possible. Now, combined with the information about trisomy, we finally had a viable, albeit invasive, method for screening for aneuploidy. And amnio remained the mainstay of aneuploidy screening for the next 25 to 30 years. But like I said, it was invasive, which was particularly true in 1972, when ultrasound was first used to guide needle placement. Prior to that, all we could do was palpate the uterus, pick a spot, and then hope we didn't cause an abruption, hit the baby, or worst of all, put a hole in the cord. Given these risks, it was first only recommended in women at elevated risk of having a pregnancy affected by trisomy. The historical cutoff was 35 years or older, and we're going to come back to that later because it plays an important role. Later, as amnio became safer due to experience and the availability of ultrasound, many people and organizations started advocating for offering universal amniocentesis. Now, this could have been the be-all, end-all of perinatal screening. It is almost 100% sensitive and specific, but the risk was high enough in the early days that people started to look for non-invasive means. Ultimately, we would find one, but it was completely by accident. It really comes down to a persistent woman who had delivered a baby with trisomy 18. If she hadn't pushed for answers, then the relationship between aneuploidy and alpha-fetoprotein may have gone unrecognized for much longer. But I'm getting ahead of myself. Why are we even looking at alpha-fetoprotein? Well, why don't we start at the beginning of that? And that begins in 1944 with Kai Olof Peterson. Peterson worked in Sweden with Dr. Theodor Svedberg, who had won the Nobel Prize a few years earlier for his work on separating colloids by use of a new invention of his called the ultracentrifuge. He proved that molecules would settle in different layers according to their size. And working with the ultracentrifuge, Peterson discovered that there were different proteins appreciated when comparing calf versus adult cow serum. He labeled this molecule phytoin, and his work was published in 1944. His discovery kicked off the hunt for more of these quote-unquote fetal molecules. The next event in our story occurs in 1956, when Bergstrand and Czar found a new molecule in between the albumin and alpha-1 globulin bands in neonatal serum. Many others confirmed their findings over the next 9 years, and in 1965 we get the first use of the word fetal protein to describe it, by Tatarinov and Abelev. Around the same time, another lab found that this molecular band could be separated out into two different molecules, which they called alpha and beta, but they didn't say which one should be which. A year later, when Dr. Gitlin published his paper on fetal protein, he arbitrarily decided to say it was the alpha compound, and so the world has known it as alpha-fetoprotein from then on. Regardless of what we call it, we now had a fetus-specific protein that could be studied. A whole host of other fetal-specific proteins have been found and can be divided into three categories: circulating proteins, intracellular substances, and enzymes. For our purposes today, we are only going to be talking about circulating proteins, as these are the ones that can be easily detected antenatally. Some other examples of circulating proteins that are only present in the fetus, or at least in substantial amounts, are fetal hemoglobin, beta-fetoprotein, alpha-2H globulin, and I think, unsurprisingly to many of you, HCG. Now, in and of itself, knowing that there are fetal proteins that are different from maternal proteins is useless from a clinical viewpoint, unless we can assess their level in some way. Well, as it turns out, due to the permeability of the placenta and absorption through contact with amniotic fluid, a small amount of these molecules do seep into the maternal blood supply. The amount that gets through is dependent on the fetal levels. This is another example of how we can get lucky sometimes in science. So it happens that AFP is one of the most prevalent molecules in fetal circulation. In humans, AFP starts being produced by the yolk sac at 4 weeks of gestation. As the yolk sac disintegrates at around 11 weeks, the production of AFP shifts to the newly formed liver. In other animals, the GI tract produces a significant amount of alpha-fetoprotein, but not so much in humans. The liver ramps up quickly and brings the fetal concentration from 70 micrograms per ml at 6.5 weeks to 3,000 micrograms per milliliter at 14 weeks, and that's when its concentration peaks. The concentration then drops off from 14 weeks till birth, due primarily to an increase in blood volume, not, however, a decrease in production. The increased amounts of AFP leach into the maternal blood supply at exceedingly low amounts. However, because non-pregnant adult concentrations are so low, it is possible to detect this slight increase in pregnant women. So we happened to get lucky, and one of the first fetal-specific molecules that we were able to identify also happens to be one that we can detect in maternal blood. Without this happy coincidence, it may have taken much longer to develop the screening that we did. Now we're almost at aneuploidy, but before we can get there, we need to take a detour through neural tube defects, because this is where AFP got its start. By the late 1960s, it was accepted that AFP could be found in maternal serum, but the current technology of the time, gel diffusion, had a hard time detecting the small amounts seen in normal pregnancy. Now this ties back into a previous episode, but the key to detecting these small amounts was radioimmunoassays. If you remember, that uses radio-labeled antibodies to determine small amounts of molecules. It was invented by Yalow and Burson from their work on insulin and rapidly changed the biomedical world. In any case, with radioimmunoassays, it was found that fetuses had levels in the milligrams per ml range, amniotic fluid had AFP levels in the microgram per ml range, and maternal serum had it in the nanogram per ml range, with normal maternal values of 125 nanograms, 250 nanograms, and 500 nanograms for each of these trimesters. Now, without the invention of the radioimmunoassays, there is no way that we would be able to detect these small amounts in maternal serum. Now, when talking about neural tube defects, the types matter because open neural tube defects allow unrestricted leakage of AFP into the amniotic fluid and lead to maternal concentrations 5 to 10 times higher than in cases without. The smaller the defects, the less increases to be expected, and the small span of bifidas may be missed, especially earlier in pregnancy. At that time, elevated values were confirmed with amniocentesis, and severe anomalies could be identified. This allowed the woman to choose to undergo a termination if she so desired, and marked a turning point in obstetrics. For the first time, women had access to information about the health and prognosis of a fetus prior to birth, and could choose to intervene if they would like to. Developments in ultrasound have changed this algorithm because we have now able to detect much smaller and smaller abnormalities, but AFP has remained an important component of fetal screening since 1974. It was, in fact, all this work on AFP and neural tube defects that led researchers to the link between elevated AFP and chromosomal abnormalities. This was already some inkling of this back in 1974, but the data was very sparse. It would take 10 years before 2 studies would come out in the same month, April 1984, before the link could be confirmed. One paper was from Cuckle et al. And published in Lancet, and the other was from Merkatz et al. And published in AJOG. I'm going to talk about the second paper more because it honestly has a more fun story, but Cuckle and his group are going to come up a lot because they published an ungodly number of papers on this subject. But let's go back to Merkatz and the persistent young woman I was talking about earlier. In December of 1982, a 28-year-old prima gravida woman underwent a cesarean delivery at 38 weeks for severe IUGR. After birth, multiple fetal anomalies were found, and a karyotype confirmed a diagnosis of trisomy 18. Now, during her pregnancy, a genetic amnio was discussed but not offered, given her age, under 35. She did, however, have a maternal AFP. Her AFP levels were found to be below the level of sensitivity of the test. Now, the mother, after the delivery, latched onto this and repeatedly asked the doctors if this was related. Now, from their paper, it would seem that they investigated this mostly in an attempt to satisfy her that it was not. But what they found instead, when they went through her records, was another woman who gave birth to a baby with trisomy 18 who also had undetectable levels of maternal AFP. Now, like I said before, the level should be low, but there's definitely an elevation in women who are pregnant, and in these 2 women, they found no elevation whatsoever. Well, now, their interest was piqued, and they started to look through their records in more detail. They ended up comparing cases from Einstein Medical Center in the Bronx and cases from the Cleveland Clinic in Ohio, and then comparing them to over 40,000 normal pregnancies whose AFP levels had been performed at the Stony Brook Neural Tube Defect Laboratory. 287 that were affected by trisomy 21, 15, or 18 were included. What they found was that there was no pattern in AFP levels in the amniotic fluid, but that serum AFP had an easily identifiable pattern. Of the 15 with trisomy 18, 3 also had neural tube defects and were excluded. The remaining women almost universally had MOMs, or multiples of the median, below the median, with some, like the index case, being completely undetectable. For trisomy 21, they found a similar but less remarkable pattern. Now, in this study, they didn't come up with cutoffs, nor did they really understand why AFP levels were low, but they knew they were onto something. The next step was to combine AFP with maternal age, because it was well known already that trisomies increase with increasing maternal age. A study by Douglas Hershey et al. In the Green Journal in 1986 tried to do exactly this. They looked at 165 cases of T21 with available serum AFP data and compared them to 36,000 unaffected pregnancies. Pregnancies complicated by T21, again almost universally had low maternal AFP levels, but the catch is that 5% of the normal pregnancies also had AFP levels less than 0.5 MOMs. This made AFP alone not a great screening test because the false positives are going to be so high. Well, next they looked at both age and AFP together. For age, they found that 1 in 365 pregnancies in mothers over 35 would be affected by T21. They use this as a cutoff for increased risk. Again, we see this age greater than 35 being used as a cutoff, and it's important that we understand that that cutoff is somewhat arbitrary. In any case, then for each gestational age, they found the MOM that gave the same risk. For example, at age 32, it was any MOM less than 1. For age 30, it was an MOM less than 0.8. For 25, less than 0.6. And for 20, less than 0.4. Now, this was promising, but as the authors themselves noted, it was a small number of women, and they recommended it be studied further before anyone started using it. In the next several years, there were several groups that published their findings, but I want to skip ahead to 1987 in a paper in the British Journal of OBGYN by Cuckle and his group. Their paper is interesting because they looked at 6 different screening algorithms that varied by AFP, multiples of the median, and age. For each age group, they found the highest AFP at which certain thresholds of risk were met. I know that is a confusing sentence, so let me try to explain it a little bit better. As an example, for age 35, they found an MOM of 0.46 or lower was associated with a 1 in 150 chance of Down syndrome. For a risk of 1 in 350 chance, it was 0.79 MOMs or lower. They did this for each maternal age from 28 to 45, and if you look at that table, it's table 6 for those of you who actually want to look at it, you notice something interesting for the 40 and older group. At those ages, a normal, meaning 1 MOM, or even a high AFP was associated with a minimum risk of 1 in 150, just because the age alone is such a great risk factor. This is going to be important later when we start talking about modern screening plans. In any case, they then looked at the false positive and negative rates for each of their 6 screening plans, which varied by the risk cutoff used, meaning that they chose AFP values that when combined with age gave risks of 1 in 100 up through 1 in 350 for ages 35, 38, and greater than 40. And they concluded that using a cutoff of 1 in 250 gave the best detection rate for women greater than 35 with an acceptable false positive rate of 5%. Now, like the age, let's keep an eye on that false positive rate of 5% because it's going to come up again. With this information in hand, the authors recommended that we use AFP and age to determine risk because either AFP or age alone have much higher false positive rates. But the main reason I wanted to bring this paper up is because of the way they chose their AFP cutoffs based on their false positive rate. There is a push and pull between sensitivity and specificity, as I'm sure most of you know. In this case, they chose a false positive rate of 5% and use that as a determination for their cutoffs. And that is a little bit arbitrary, and we're going to see that 5%, like I said, throughout the rest of these papers. Now, the use of AFP was just beginning, though, and by 1988, the same group had started investigating both estrogen and beta-HCG levels. The rationale behind estrogen is interesting. Now, AFP is made in the liver, like I said, and so Dr. Couples' group started to look at other compounds that required the fetal liver to see if they followed a similar pattern. They went and looked at stored mid-trimester samples from AFP testing in 22 women from New England. They found that, like AFP, estrogen levels were also below a MOM of 1 in the majority of women with trisomy 21. The same group then looked at HCG after a 1987 paper reported elevated values in a small sample of women with Down syndrome. In another retrospective study, Cuckle's group found that the majority of women with a Down syndrome baby had an MOM greater than 1 with a median of 2 MOMs. They next looked at combining AFP, estrogen, HCG, and age together. First, they looked to see if they were correlated to each other, which would make them confounders and therefore not additive to the screening. They found that they were not, and so they looked at combining them all together into one test. The main benefit found was that each additional test reduced the false positive rate. So let me give you some numbers for a 35-year-old woman. What I'm going to give you is the detection rate for Down syndrome while keeping the false positive rate at 5%. Using AFP alone would detect only 30% of cases. Estrogen alone, 40%. Beta-HCG alone, 50%. Or all three together, 60%. Still not as great as we'd like it, but each additional test decreased the false negative rate significantly. Now, this paper still only had 77 pregnancies affected by Down syndrome, and so bigger studies were needed. But it showed that age alone was not a great screening mechanism for who needed an amnio, because remember, that was the next step for most of these women. Now, both women under 35 and over could benefit from screening to both increase and decrease the number of amnios performed in each group. At this point, we're starting to look like modern screening. What was just described is essentially the triple screen. Further prospective studies, many performed by Dr. Cuckle's group, through the early 90s showed that the initial numbers were correct and programs using all three were started. Now, the next major advance was the addition of nuchal translucency. Up to now, all of this screening was performed after 14 weeks. By the time the serum screening and amnio was done, women were at 18 to 20 weeks, which led to kind of late-ish terminations, which does increase the risk for the woman, and people wanted to find ways of detecting this risk earlier. By the late 80s and early 90s, it was known that cystic hygromas were often seen in the second and third trimesters in babies with Down syndrome. And so in 1992, a group headed by Nicolaides published a paper looking at the significance of nuchal edema and hygromas in the first trimester in babies diagnosed with aneuploidy. They found that a nuchal fold greater than 3 millimeters significantly increased the risk of aneuploidy. In specific, they found that 35% of babies with aneuploidies had an abnormal NT, and that only 1% of normal babies had a thickened nuchal fold. Now, around this same time, Cuckle's group, there he is again, was also investigating pregnancy-associated plasma protein A, or PAP-A. Like estrogen, they found that pregnancies affected by aneuploidy were likely to have much lower levels of PAP-A. What's more is that these levels could be detected in the first trimester. Now, for the reasons I went over a minute ago, there was intense interest in this first trimester screening, and so several groups started to look at using all 4 analytes together in the first trimester, and found that it was possible. And by the late 1990s, people were combining these together with the NT. One paper from Wald et al., published in 1997, showed that combining these analytes increased the detection rate to 80%, while again keeping the false positive rate at 5%. So you can see the steady progression from 30% to 80% detection rates as we add more and more factors to the calculation, and we're not done yet. There's one last development in this chain to talk about, and that is the integrated test. A 1999 paper by Wald again does a nice job of putting all these stats together, and so I'm going to quote from that paper. Now, they set the false positive rate at 5% again, and compared the sensitivity of 5 different screening approaches. Those are second trimester AFP and HCG, or the double screen, AFP, HCG, and estrogen, the triple screen, or AFP, HCG, estrogen, and inhibin A, the quad screen. Now, I know I didn't talk about inhibin A because I felt we're getting a little repetitive, but suffice to say that it does add to the sensitivity like everything else does. All 3 included age as well, and they found a 59%, 69%, and 76% detection rate, with the false positive rate being held at 5%. Then they looked at the first trimester combined test that included PAP-A, HCG, and NT, and lastly, an integrated screen that included first trimester NT and PAP-A, and a second trimester AFP, estrogen, HCG, and inhibin. There they found detection rates of 85% and 94%. Well, now that sounds great, but there are some pros and cons here. The whole point of the first trimester test was to make a diagnosis earlier in the pregnancy, and even though the integrated was better, we were going back to a second trimester diagnosis and the issue that came along with that. So, people developed 2 methods for using the integrated approach but getting a result after the first trimester portion. Now, before I get into that, it's important to remember that the first trimester portion of the integrated test is different than that in the combined first trimester test. The combined has NT, PAP-A, and HCG, while the integrated only has NT and PAP-A. So we are, by design, getting an inferior result after the first trimester with the integrated test. Now, with that caveat, the 2 methods were called the stepwise and the contingent sequential tests. In the stepwise, the first trimester result would be provided to the patient, and then the final risk would also be reported after the second trimester portion. Now, this did give women access to a risk earlier, but also meant that she might act on less accurate information while she waited for the second part. In the contingent method, a negative first trimester result would result in no further testing. A positive result would result in an amnio, and only women with an intermediate result would go on to the second part. This was designed to maintain the detection rate of the integrated while also offering earlier results and intervention. In theory, this made a lot of sense, but in practice it proved to be very complex with poor patient follow-up, and most centers have abandoned this approach. Currently, ACOG supports all of these methods and recommends that screening be offered to all women. When choosing a test, it really comes down to a trade-off between detection rate and when the results are available, as well as the complexity of the screening algorithm. To review it once again, the first trimester combined test has a detection rate of about 85% and can be done as early as 12 weeks. This quad screen, which can be done at 15 weeks at the earliest, has a detection rate of about 81%. The integrated screen results in a similar time frame, about 15-16 weeks, and has the best detection rate at 96%. The sequential and the contingent give 2 results with a combined detection rate of 88 to 95%, but also has that increased complexity and cost. So how do we decide? Well, unfortunately, there is no right answer. At my institution, we use combined first trimester screening, and we accept the slightly lower detection rate. I should also note that the combined is the only test that does not test AFP, and so it's important that if you do a combined test, you also do an AFP at 15 to 22 weeks to screen for open neural tube defects, which is where this all started. Now, before I finish today, I want to go back and address that 5% false positive rate. As I mentioned before, this is completely arbitrary. For the false positive rate, what we are really talking about is the number of women who undergo an invasive test like an amnio and get a negative result. A 5% rate means that for every 100 women who have an amnio, there are 5 who didn't need it. Now we can change this rate by accepting a lower false negative rate, and where we fall on that balance between false negative and false positive rates depends upon your views of the risk of an amnio. Now, I'm going to hold off on that in-depth discussion about invasive testing until the next episode, but I want everyone to think about how we choose our cutoffs, because this is not something that the women get to decide. We decide for them, and it's not something I really thought about until the rise of cell-free DNA, which is also going to be covered in the next episode. Well, I hope that wasn't too confusing, and I hope I gave you all something to chew on. I can't wait to get to the next episode, because I do have some really strong feelings about cell-free DNA. Now, if this sparked any questions or thoughts, then please feel free to get in touch with me at feedback@obgyn.fm or in the Slack group. And as always, if you want an invite, just drop me a quick note at that email address and I'll get it to you. Lastly, we've been doing this for over a year now, and I want to hear from the community what you'd like to hear more of. A lot of times it feels like it's just me speaking out into the void, and I would appreciate any feedback that everyone has. In any case, we'll be back soon with part 2, and until then, as always, thanks for listening.